How we doing, folks? Make sure we're recording, and we are. Good, good, good. Got my new dock cam system set up here, and I've actually got keep this where I can kind of make sure I'm still in the frame here. The only issue that I'm really still dealing with is I've got a little bit of shadow issues that I've got to deal with, but I'll think about how I can do that. It might not even be an issue at all in my office, but we'll see. So I want to move on to the set supplements that we've already taken a test over this. This was on our test 1. But I want to continue on with this, and if you had issues with these proofs, make sure that you know how to work them. So this is a little bit of review for us all. So let's start with problem 1 out of the set supplement. We're told that A is a subset of universal set, which pretty much goes without saying, and that we want to show that A union A complement is equal to the universal set. Part of this we already know. Any set would be a subset of a universal set. So we know that A union A complement is a subset of universal set. So we're halfway there. Remember, the way we prove the sets are equal is we show that one side is a subset of this side, and this side is a subset of this side, and so that means they have to be equal. It's kind of like when we do x is less than or equal to y, y is less than or equal to x. Well, the only way that can happen is if they're actually equal to each other. Okay? So now let x be some element in U. Okay. Now there's two choices there. It's either in A or it's not in A, right? So we have to check each of those cases. If x is in A, then certainly it would be in A union anything, right? And that's what we have to do, is show that anything over there, if x is not in A, then that means it's in A complement, and that means that it's in A complement union with anything, right? The set of all cats, it doesn't matter. So A union A complement. So then either way, either case, we know then that x is an element. They start over here is an element over here. We now have U is a subset of A union A complement. So one final statement then, since we have the double set inclusion, this is a subset of this and this is a subset of that, they are equal. Okay? And that's really the way these set proofs go. The next one, 1b, actually shows you a slightly different type of set proof when we're trying to show that something is equal to the empty set. What you can't do here, empty set is going to be a subset of anything, but you can't show that things are in the empty set because there's nothing there, right? So typically when we're trying to show that something's equal to the empty set, this would be a proof by contradiction, right? We'll say, well, suppose there is something in there, and then show that something goes crazy, right? So you may want to pause here and do your own kind of thing for a moment. If not, let's go through and talk about how we do this. So let's suppose that there does exist an X that's in A intersect A complement. Now what that means is and, right? X then is in A, and X is in A complement, excuse me. But then that means that X is not in A. So X is in A, but then also not in A, and this is a contradiction. Thus, there are no elements in A intersect A complement, meaning that A intersect A complement is the empty set. So there's a little variety for you, showing you two different types of proofs. You know, if there can be things in there, that's great, then there they are. If we're trying to show it's an empty set, we just have to show that if we pretend there's something in there momentarily, it'll automatically cause a contradiction. Okay? All right. Then let's look at 1C. Here we're going to show that A minus the empty set is still A. It makes sense. There's nothing in the empty set to take away, right? But let's talk about the proof. This is something we would do with double set inclusion. So let's let X be some general element in A minus the empty set. Okay? What does that tell us? Well, then X is in A in particular, and that's all I need. It also means it's not an empty set, but who cares? So this X that started over here is in A, and that means that A minus the empty set is a subset of A. Okay? Halfway there. Now, let X be in A. We know that X cannot possibly be in the empty set because it's empty. If it's in A but not in that set, then X is an element of A minus that set. And that means that A is a subset of A minus the empty set. So you've got this is a subset of that, that's a subset of this. Therefore, A minus the empty set is equal to A. These are not hard proofs, right? The hard part is that they're so simple that you need to make sure that you don't assume something that you can't assume, right? So I think it's just a question of us going through there and kind of, you know, stating things clearly and covering all our bases. Okay, forgot to make them a little box after to it. Okay, the last the last part of problem 1 was prove that the empty set minus A is still the empty set. Okay, again, if we're going to show something's empty set, then that's most likely a proof by contradiction. Now, you can stop here and give it a try if you haven't already. Okay, but that's the way I would approach it. Let's suppose for just a moment. Suppose that there exists an X that's actually in the empty set minus A. Then X would have to be in the empty set, right? A contradiction. Thus, is empty, and that means equals empty set. Okay. Again, not a quick thing to, not a very difficult thing to show. You just have to be careful and do it correctly, right? Okay, let's move on then to problem 2. 2A, we're dealing now with 2 sets. In problem 3, we'll deal with 3 sets. But in problem 2, we got A and B, and we want to show that A minus B is still a subset of A. Now, we're not doing double set inclusion, we're just showing a subset one way. So, pause right here if you haven't worked it already, if you want to go through this. Otherwise, the proof would look something like this. We let X be something in A minus B. What does that mean? Pause here if you want to write that out. If not, then X is in A, but X is not in B. And X being in A is all we needed. Then A minus B is a subset of A. That's all we needed. One line. Hope that's okay. Now, again, let's show that this intersect that is in the empty set. We're not going to say let X be in this, right? We're going to say, if to prove this, we're going to have to show that there cannot be an X in that. So we might actually, again, do a proof by contradiction. Suppose that there exists an X in A and B minus A. And X is in A, and, sorry, I don't want to move the paper, my bad. And X is in B minus A. If that means then X is in B, but X is not in A, and that is a contradiction. We said it was in A. Therefore, this thing that we suppose there was an X in, there is no X in there. Sorry. A intersect B minus A has no elements. Thus, it's the empty set. Okay? Hope you're getting a flavor for these. They're pretty straightforward, and you're kind of getting a swing of them once you get going. All right, this is actually one of De Morgan's laws, the notion that the complement of the quantity A intersect B is A complement union with B complement. Okay, these are 2 sets that are equal to each other, so we're going to have to do the double set inclusion thing. So let's set out to do that. Let's let X be in the complement of A intersect B. What that means then is that X is not in A intersect B. Now, we have to think about this just a little bit, and this is where scratch paper sometimes comes in handy. I'm going to do it right over here to the side. If we think about a Venn diagram with A and B, here's A intersect B. What I'm saying is, it's not in there, okay? Well, there's 2 ways I can describe what's not in there. I can talk about things that are outside of A, okay, and leave this part out. Or I can talk about the things outside of B and leave this thing out. But when I say or and put those 2 together, that's getting to it, right? The other thing we could do, I guess, is look at the different cases that we have. Okay. For it not to, the only way it can be in this is if it's in both. There's actually 3 things that could happen, so it's not in there, right? It could be in A but not in B. It could be in B but not in A, and it could actually be in neither one of them, right? But the two cases really that you can talk about is just say, well, then it's either outside of A or outside of B, right? So then X is not in A, or X is not in B. And that actually covers all three cases. Okay. Now you know with OR, we have to look at those are cases, so we have to look at those two cases. If X is not in A, then that means X is in a complement, right? And it would be in the union of A complement with anything, the set of all dogs. Sorry, Bentley. A complement union, certainly with B complement, right? If X is in or not in B, then X is in B complement, but then it would be in the union of B complement with anything, and in particular, A complement. Thus, since anything we took over here ends up over there, that means that A union B complement is a subset of A complement union B complement. Okay? Now, let's go the other way. So there'd be something over there, then X is not in, it's in A complement, or it's in B complement. Okay? If it's not in A, now, and is one of the things we can actually kind of deal with not an element of, right? Because it's and, it has to be both. If, sorry. Oh, and this is what I typically do down here. So if X is in a complement, then X is not in A. And if it's not in A, it certainly can't be in A and anything else, right? So that means X is in A intersect B complement. And if X is an element of B complement, then X is not in B. The phone. Sorry. Okay, sorry about that. Okay, so if it's not in B, then there's no way it can be in A and B, right? Then X is in the complement of A and B. Thus, I'll save a line here, thus A complement union B complement is a subset then of A intersect B complement. And then the last thing you say is, well, then therefore, since we've got double set inclusion, that A intersect B complement is A complement union B complement. Boom. Okay. See what we're doing there. And then part D of 2, Okay, we're trying to show two sets are equal. We're going to do the double set inclusion thing. Okay. So let X be some element in A union A intersect B. Okay. Then X is in A, or X is in A intersect B. Well, there's two cases here, but one of them is actually what we're trying to show is that X is in A, right? So that one I'm not worried about. If X is in A intersect B, then X is in A and in B. But the big thing is that it's in A. So then there's no doubt that this stuff on the left is a subset of A. Because whatever thing we chose ended up in A. It's either A here or A there, right? So now, let's go the other way. Let X be in A. Okay. This is pretty quick too. If it's in A, it's in A union anything, right? Sorry, my dog's just agreeing with me. And so A is a subset of A union A intersect B. Okay. Therefore, since we've got the set inclusion one way and the other way, we know that they are equal. Okay. Very good. Let's do a couple more. We'll finish up problem 2 and then we'll call it quits on this one. Let's prove that A intersect the quantity A union B is also A. Same basic process, right? We're going to take something over here, show it's over there, something there, show it's here. Alright, so let X be an element of A intersect A union B. Then X is in A and X is in A union B, but X and A is all I needed. Oops, sorry, didn't need that at all. So I know that this is a subset of that. Okay? Now, let X be an element of A. Well, I know it's in A, so that's this part. To be in the intersection, it's got to be in this part too, but this is a union. So then X is definitely in A union anything else. And then X would have to be in A intersect this, intersect that. So then we have A is a subset of A intersect A union B. Since you have the set inclusion both ways, they're equal. Okay? Hope you're following what we're doing here. Alright, one last problem here. Okay, I'm getting a lot of sound from downstairs. Let me go shut that door again. I'm sorry. There we go. that's the one thing I noticed is I can't with the other thing I could pause it right there on the spot. That's all right. I still say the advantages outweigh the disadvantages. So let's do this last problem. Let's let x be some element in this stuff on the left here. A intersect B union with A intersect B complement. Okay? Then that means that x is in one or the other, possibly both. Okay? So we have to check those cases. If x is in A intersect B, then x is in A, which is really all I need, and x is also in B. If it's in A, we took something here, showed it's in A, then that means that this... Oh, wait, I want to check both the cases first. Sorry, so let me not do that yet. If x is in A intersect B complement, then again, x is in A, which is really all I need, and x is in B complement. Either way, we know that A intersect, oops, sorry, got it backwards, sorry. Union A intersect B complement is a subset of A. Okay, now let's go the other way. Now let x be in A. Now there's no mention of B here, right? But we know that it's either going to be in B or not. It's in B or x is not in B. So we check those two cases. If x is in B, it's in A and it's in B, then x is in A intersect B, and that would put x actually in A intersect B union with anything, but in particular A intersect B complement. If x is not in B, then x is in B complement, and x is in then B complement union, and it's in A and B complement, so x is in A intersect B complement. Then it's in the union of A intersect B complement and anything, but in particular this stuff, right? Okay. So what we're saying then is that A started in A, ended up here. So A is a subset of A intersect B union with A intersect B complement. So since we have the double set inclusion, ignore this, therefore A intersect B union A intersect B complement is equal to A. Okay? So that gets us through problems 1 and 2. I'm really kind of liking this little dot camp thing I got going here. Hope you are too. Hope the sound is better. So I will stop right there, and we will pick up with problem 3 next time. See ya.